Roberto.
Hello, everyone. It's a pleasure for me to introduce a friend and a collaborator, Hugo Parada Hughes. Before we start, let me just give some words about Hugo. Hugo finished his PhD in the Grenoble Laboratoire Guzman under the supervision of Emmanuel Crépeau and Christophe Prier. Also was students of Eduardo Cepa and Patricio Guzman in the master in the Federico Santa Maria University. And also, Hugo will talk a little bit about boundary observation of the KdV equation graphs. Hugo is an expert in control theory, more precisely stability and control theory of coupled PDEs. Hugo, thank you very much to accept this invitation.
So thank you, Roberto, for the introduction, and also thank you to the organizer for giving me this opportunity for the invitation. So as already well said, Roberto, I want to speak a little bit about this joint work with Roberto and his now doctor, the past PhD student, Jean Davidson Santos da Silva, about boundary observation of the KdV on graphs. And just to be a little more clear about a little introduction of that, just to mention that PDEs on network we can use to model a lot of systems. For instance, here I have a picture which is the network, the graph we say, of the gas distribution in France. And usually to model this kind of networks, you use graph where the node of the graph represent the interconnection of the networks. And in this context, the control and stabilization problems have been widely studied and also are very natural. For instance, I also would like to see, for instance, if here in this city, we need to fix a quantity of gas, we know some quantity of gas, and we already have bulbs here, so the control would be good enough to travel around the network to arrive to fix the good quantity here. This is like the idea, the motivation. So the focus of this talk is about KdV equation and graphs. So we want to pass to more theoretical results. So for those who don't know, the KdV equation is the following one. Is the Korteweg debris is a one-dimensional, third order nonlinear equation, and was introduced by Boussinesq, but it gives his name by Korteweg and debris to model the propagation of long water waves. So here U represent the deflection to some reference level, and you can model the propagation of this wave using this equation. Also, you can use to model a lot of other systems like water waves, tsunamis, etc. With respect to the control of this equation, we have a lot of results, a lot of literature. The first one are given in the periodic framework by Russell and Sang. And in the not-periodic framework, if you study this equation in a boundary domain, the first work is the one of Rosier. This is actually one of the references that we want to use in this work. You also have several of the results in the nonlinear system for periodic framework, for measurable sets, etc. by a lot of research like Coron, Crépeau, Serpin, Nguyen. Robert also have a lot of work of that. So the problem that Rosier considered is the following one. You have the nonlinear KdV equation, which is posed in a boundary domain, we say 0L. You have Dirichlet boundary condition at the left and at the right, and you put a control in the Neumann right boundary conditions. So the idea is the following one. You have first, as is classical in control theory, we study the linear system, so we consider the linearization around 0. So you have this linear equation, which is the same with the same place of the control. And you ask the controllability problem, which is the following one. You have an initial data, U0. You have a final data, we say UT. And the idea is to find a control, H, such that the solution of this system satisfies that in time t, capital T, is equal to this parameter UT. So you can study this problem in the following setting. You can define an operator that take a control and associate for each control the final data. So here it's important to recall that for this equation, you can also define which is called the adjoint system, which is a system which is reversing time. And you have to take care here you use another boundary condition because to reflect the boundary conditions. So why this adjoint system is important? Because we are interested in controllability problem. So for the controllability problem, we are asking if this map, lambda, is surjective. So the exact controllability means if this lambda is surjective, so you can maps for all of these UT, you can find a control that satisfies this condition there. And the surjectivity using classical functional analysis method can characterize using the adjoint of this operator. So here, so the exact controllability is equivalent to this inequality. So you can measure, you can observe the final data of this adjoint system using this quantity there. So in this particular case, this quantity there, you can make some computation and see that it's just the Neumann trace at the right. So the result that we have here that the system is exactly controllable if and only if this inequality, which is called the observability inequality, you can observe this data using this measure, is true. So the idea of Rosier is the following one. You have this inequality, you want to prove this inequality, you suppose that this inequality is false, use a contradiction argument, and actually you can see that it's enough to study the stationary problem. So you have the stationary problem, and you suppose that this inequality is false, using some compactness, some regularity result, you arrive to an overdetermined system. You have like the same boundary condition plus an extra one. And as you are doing contradiction argument, you can ask if there exists solution of this system. If the only solution of this system is a trivial one, you're okay, you win. But if you have solution of this overdetermined system, you can find solution that disprove the observability inequality. So to do that, Rosier take Fourier transform of this equation, and at the end, study what happened with the Fourier transform of this function phi. In this case, you arrive to something like that. So this function phi is well defined. You have a non-trivial solution if you can pass this polynomial here by dividing, and then you need that all the roots of this polynomial to be also roots of this complex function. So if you do some computations there, because the roots of this complex function are quite easy to find, are periodic, you arrive to the next condition. So the observability is true if and only the length of the bounded domain does not belong to this set, which is called the set of critical lengths in the Neumann case, which is quite good in that case, and you can explicitly characterize that set. So that's the idea of OSI. In this setting, some years after, Glass and Guerrero study a quite similar problem, but now you put the control on the Dirichlet right condition. So if we remember, the control of Rosier was in that condition. So here again, the adjoint system is the same, but now the observability inequality is quite different because the operator is quite different. So now you need to measure the final data using this trace. And again, in that paper, Glass and Guerrero would prove that the observability is true if and only if the length does not belong to another set of critical lengths, what I call the set of critical lengths Dirichlet. And in this case, you cannot explicitly characterize. It's only given by some complex relation. This is like the history of the KDB, which is the main idea of the method. So now we pass to what happened with KDB on graphs. So the model that we used to, in a mathematical way, was motivated by the following work of Emmanuel Cripot and Michel Sorin, that they used KDB equation to model the pressure in an arterial compartment. So then a natural extension is to study what happens if in an arterial tree. You have like your heart, you have arteria that start from the heart. So we want to study here is like a simplification of that for sure. You have here a central node. You have some branch. On each of these branch, you have a KDB equation. And here you have some coupled conditions. So which are these conditions that we want to consider? So again, if you consider UN the deflection of the water wave in the network, and you take Vn its velocity, so here UN will satisfy a KdV equation, and the velocity, if we follow the work of Whitman, is given by this expression. So a natural condition to ask in the network, if you imagine the network here, you can ask for continuity. So all the solutions are the same in the central node. And you can also ask for a way of null flux, that in the central node, the flux is null. So if you compute a little bit about this condition of the null flux, you arrive to this boundary condition, which is given here. So then we join all the stuff that we have, and the system that we can study is the following one. So we want to really have a KdV equation. We consider only linear system, have a KdV on each branch of the network. We have continuity conditions, so all the solutions are the same at the central node. We have this condition which is related to the flux. And we have also put some Dirichlet and Neumann control at the right. We have control here, and we also put, just to speak about the model, a control in the central node. So in this framework, we have some results already. That I was studying a work of Kaisa Mario and Manuel Kripo, and also of a work of Eduardo Setpa, Manuel Kripo, and Claudia Moreno. So what do we know about the system? So here first, we consider a particular case with this parameter alpha. We put n just to simplify the computations. So if you imagine the same idea of Rosier, you take the system with all your controls, you start to see which is the observability inequality associated to this controllability problem, you arrive to the following one. So trust me, this is the enjoy system. You may just do integration by parts and you compute and you get this enjoy system. If you see, you have like this reverse KdV equation, continuity. This is like the joint boundary conditions with respect to the flux. We have this also extra condition, which is quite similar to the one that we have for the KdV. And the observability, in this case, is the following one. You can measure the final data using information of this trace that comes from the control on the Neumann condition, this one that comes from the control in the Dirichlet condition, and this one that comes from the control in the central node. So again, if you do like Rosier idea, you suppose this inequality is false, so you win a lot of extra conditions and you try to choose if there is some solution of this overdetermined system. So first, to work in this case, we need our post result. So now I want to present I like this idea, it's a clever idea that Jadairson had. So first to define this space, which is like the classical space for KdV, continuous H1 of the network, L2, H2. So for the joy system, you can prove the following regularity. So don't be afraid to have this regularity, and you can also well estimate the trace of the equation. So if you see these two terms are like the one that appear in the observability inequality, and which is very important here, we also have this estimate, which is like the sharp cathode smoothing effect for the KdV equation. So the idea is the following one. If you use semigroup theory and classical multiplier estimate, you get this one. So you get already the continuous H1, L2, H2. You get this trace, and you can also estimate the central node condition. So just to fix ideas, I want to show a little bit idea in the case of where all the lengths are the same. So if all the lengths are the same, you can define the sum of all the components of the branch. So if you see what the equation satisfies the sum, okay, satisfy a KdV equation. As all the solutions are 0 L, this condition we have, as all the solutions satisfy that the derivative in 0 is 0, you have these conditions. And if you remember the condition of the flux, you have this one, which is quite cool. So if you saw the estimate that gives us the multiplier method, have that this term is in L2. And for this equation, there is an existing regularity result that tell you, okay, this function C satisfies the Sharp-Cató smoothing property, this regularity. Cool. So we have a regularity estimate for the sum. Now we study what happened with a function key, which is the difference of the one in one and the other branch. Why we do that? If you remember, this function we satisfy a KDB equation, but by the continuity condition, this one is the same as this one is 0, so you win this condition equal to 0. So for this one, they have these boundary conditions, and again, it's a known result that for this function you have the Sharp-Cató smoothing effect, this regularity estimate. So the clever part now is you can write phi1 using all these functions that have the good regularity, and also the sum function that also have the good regularity. So at the end, you can conclude that phi1 satisfies the Sharp-Cató smoothing effect, and then you come back to all the other branch using the continuity. So you have the equation that satisfies all the other branch, and here by the continuity you have that this term that before was just in L2 now is in H1/3. So you're winning regularity, and you can prove that this branch, the other branch, satisfies also the Sharp-Cató smoothing effect. And then you have the Sharp-Cató for all the branch, and then you can do also an argument to pass to different branch. And this is the main idea of the regularity. Okay. So we pass now to study which is our control problem. You have a good framework, you have well posed. And our idea here is try to prove a controllability result without putting a control in the central node. Why? This is to be a natural question, because if you have a network, it's more natural in the sense, of the physical way, to put control outside of the network than in the central part. So you are taking measure outside of the network, in the exterior of the network. So the framework is the following one. You have a KDB equation, you have the continuity, the flux condition, the other boundary conditions, and you have n control. So you have just one control per branch. You have either a Neumann control or either a Dirichlet control on each branch. So again, if you see what happened with the observability inequality, the observability inequality is the next one. You should measure the final data using information of the trace, the ones that come from the Neumann control and the ones that come from the Dirichlet control. So this is the problem that we try to solve. So, okay, so which are the previous results about that? So the first one is the result that is given in the paper of Kais and Mariam report that say the following one. If you put control in the central node, and you also put controls in the Neumann of the exterior of the branch, you have controllability if at most you have one critical length. So it's important that here they are putting control in the central node. You have also another result that, okay, if no one of the lengths is critical, but also you put a control on the central node, you can remove a control of the other branch. You have n-1 Neumann, but what control in the central node. So in that sense, the controllability without the control on the central node is not known until the following work, which is the work of Eduardo Serpa, Merkel Po, and Claudio Monero, that they can prove controllability only with Neumann controls, no control at the central node, but they need that the maximum of the length is small, and also they need a big time. Why? Because in that work, they use some multiplier estimate to prove the observability inequality, and the multiplier estimate requires some restriction on the time and on the length. So what we can prove in our work, we can prove the following one. So we focus on the case where all the lengths are the same, and in that case, we find the sharp critical lengths for the network. So this is a big table. It's quite to be strange, but I want to see why we have this. Okay, just to be a recall. If we have just two equations, you have just two equations in the network. In one we put Neumann, and in the other one we put Dirichlet. We don't have critical lengths. So in that case, the system is exactly controllable for all lengths. Then we have other kind of configuration. If you put one Neumann and n-1 Dirichlet, in that case, you have only the critical length of the Dirichlet. Other configurations, we have only the critical length on the Neumann. We have some case, if you put m Neumann, n-m Dirichlet, the critical lengths are the one on Dirichlet and the one on the Neumann. And also, in other cases, if you put only Neumann, you also find this set, which is quite nice. You have the same set as here. And if you put only Dirichlet controls, you have the critical length of the Dirichlet case and also a new set of critical lengths. So at the beginning, this seems quite strange why we have these conditions. So I want to try to explain in the blue case. So this is like a general way. So we put m Neumann and n-m Dirichlet controls. So if you come back to Rosier idea, you have your observability inequality. And the idea is to say, okay, this observability inequality is false. You use compactness, uniqueness argument, regularity, and you arrive to a stationary system, to a spectral problem, which is overdeterminate. We have a lot of extra null boundary conditions. So this one comes from the Neumann control, and this one comes from the Dirichlet control. Okay, the idea is there exists non-trivial solution of that system. So the idea here is, as all the lengths are the same, you can define the sum of the Neumann control. So you have your network, you take all the branch where you put Neumann and you sum. And then you do like a ponderation of that sum, which is the function Cj. And you see which is the equation that satisfies this Cj. And if you see first is the spectral problem of the KDB, this one and this one, this in the black one, are just the one that come from the joint system. The blue one comes by the Neumann control, and this brown one comes by the shows of this function. Which is very, very nice that this spectral problem is exactly the same that Rosier studied. So we know that the only solution, the only non-trivial solution of this system exists if the length is not is critical. So we have that this solution is 0 if and only if the length is not critical. Okay, so if you come back, if the length is not critical, this solution should be 0. You come back to the definition, and you have that phi j is equal to 1 over m dc for all j. So that tells you that all the branch where you put a Neumann control are the same. You can see just as one equation. So you can do the same for the Dirichlet control. You take the sum of all the Dirichlet, and if the length is not critical in the Dirichlet sense, you have that all the branch where you put a Dirichlet control are the same. So this is the idea. So what we have done here, we have a network. In some part we put Neumann control, and the other part we put Dirichlet controls, and we are taking the sum. And you can, I like to do that, you can shrink all the solution, you shrink all the Neumann controlled branch to just one. And again here, you shrink all the Dirichlet controlled branch to just one. But for that, if you want to shrink the Neumann one, we should pay the Neumann critical length. And if we shrink the Dirichlet one, we should pay the Dirichlet critical length. So at the end, if the length is not critical in that sense, you arrive to just a system of two equations. And the take now is, in this system of two equations, there are no critical lengths. So the critical length comes only for this shrinking argument. So if you have that, if you come back here, this is why in the case of two equations, we don't have critical lengths. So if you have just two equations, we don't have critical lengths. And the critical length of that case comes only from this shrinking argument. So now we have to see why, in that case, we don't have critical length. This is the complicated part. So again, we consider which is the equation satisfied by these two equations, and we apply Rosier strategy. We take Fourier transform, we do some computation, integration by parts, and we arrive to that. So here we have this polynomial, which is like the Rosier one, but here the complex function that arrives here, which is in some papers called quasi-polynomial, is more complicated to study. So if you remember, Rosier one was just this part. So you know that if we have, just this part, the zeros of this part are periodic, but here you have this quadratic term that complicates a lot. So this is the one where you put Neumann control, and if you do the same for the one that put Dirichlet control, so you arrive to this one. This actually seems more tricky because you have also a C here exponential. So the analysis of the zero of these two equations is not too easy, as in the Rosier case. Which is important here. That all the parameters that appear here are related to some trace of the equation. For instance, this kappa one here is just the continuity condition. This beta Neumann, is just the second derivative in zero of the first function. This is the second derivative in zero of the n function. The delta one is some trace of the n function, and etc. It's important to recall that, but for instance, if we show that kappa is zero, you win this condition. By continuity, you win a lot of boundary conditions. And again, same, if you show that delta is zero, you are telling that this trace is zero. So you get an extra boundary condition and you can conclude information about the function. So which is the idea to prove that you only have the trivial solution here. So if you remember, you have this kind of function. So first, you should have that gamma, beta, and p should be zero, should be different of zero. Why? This is already, I said, if gamma is zero, you're winning an extra boundary condition, so you can prove that all is zero. If beta is zero, which is the difference, you have this difference equal to zero, and also this one equal to zero, so you can solve that each of these beta should be zero. If p is zero, if this p here is zero, you can solve explicitly this polynomial, and you can find explicitly the roots, and you can find some contradictions. So you can also prove that if the roots of that polynomial are double or triple, you can compute explicitly that roots, and you can find some contradictions. So we are showing that these zeros of here, zeros of that, in a very specific case. So you need that the roots of the polynomial are centered. So, okay. Other important fact is that as p is different to zero, zero is not a root of that polynomial. So now we will show that if p is not zero, the roots are simple, then we should have that delta, which is a trace, should be zero. So which is the idea? So we take a root of that polynomial, which is different to zero, because p is different to zero. So as if delta is different to zero, you have here this delta. Okay, so you have this one what comes from the Neumann controller, this one from the Dirichlet one. So here, as the length is the same for this both equation, you can isolate this term. So you can put along this term, the exponential one. So you put along this exponential one in the first equation, and you get that. And you put along this exponential term in the second equation, and you get that. And here we are using that the root is not zero, and we are also dividing by delta. Okay, we have that. So if we have these two equations, we can find a new one, because you have two expressions for this. And in particular, if this CS is a sample root of the polynomial, you can find a new polynomial one. This a third order polynomial. But okay, we have a polynomial here that had three roots which are different. We have also another polynomial that have three roots that are different, and actually are the same roots of that polynomial. So you have two polynomials that have the same roots. Those should be the same up to a constant. And for instance, this polynomial does not have the second power, no have a square term. And this polynomial have a square term. Kappa is not 0, gamma is not 0, so this step should be justified. That implies that delta should be 0. So yeah, just to recover, we have these two equations. We isolate the exponential, and then we find a new polynomial of third order as this one, which share the same root. It should be the same up to a constant. So that means that delta is 0. If delta is 0, the only solution is the trivial one, and there the controllability holds. That's the main idea. So this is the main idea to prove controllability. So just to recover, here we have Neumann controls, Dirichlet control, which shrinks, we arrive to two equations, Neumann, Dirichlet, and there are no critical lengths. So with this argument, I can explain what happened with the other part of the table. So here, in that case, you have just one Neumann controlled equation. So you cannot shrink, you have already one. So the shrinking, the idea of sum or reduce just to one, you only use in the Dirichlet controls. This is why here to pay a Dirichlet critical length only. Again here, in the Dirichlet, in that case, you have already one Dirichlet equation, one Dirichlet controlled equation, so you cannot sum up. You can just consider this one, but you sum up all the Neumann and the shrink so that you pay the Neumann critical length. So these two cases are more intricate. Here, you can do also the same idea. You sum all the Neumann one. This is why you pay Neumann controls, Neumann critical lengths, and then to arrive to a new spectral problem that should analyze case by case. And this gives you this Dirichlet case. Again here, you should pay you sum all the Dirichlet equations, and then you pay a Dirichlet critical length, and then to arrive to a new spectral problem that gives you this new set of critical lengths. So this is the idea. For finish this part, I want to show that there is more ways to show what happened with the critical length, existent or not. So this is a Kawahara equation. This is a generalization of the KDB considering fifth order dispersion. So in this case, we have the transport term, which is negative. And just now, again, we have an equation this way with 5 derivatives. We have 6 boundary conditions. So this one and this one that comes from some observability case. So for instance, it's not that case, but if you change a little bit the sign of the first order, third order, and 5th order, in some case you can find some critical lengths. Actually, there is a very recent work of Rosier studying this kind of equations. But I can show, for instance, that in that case, in that particular case that I put in here, there are no critical lengths. So the idea is the same. You study the spectral problem, which is this one, and you have these 6 boundary conditions. To apply again, Rosier idea, you take Fourier transform, and you arrive to that. So if you take Fourier transform of the function, you get a complex function that seems quite complicated, and also a 5th order polynomial. So here you have this 5th order polynomial. The key part is that this constant is real. And if you put all the roots of that polynomial here, it's just some algebra, you can isolate again the exponential and see that this function is entire, so there exists a function, if all the roots of this polynomial satisfy this condition. And if you see the left-hand side of that part, it's like a Mobius transform. So you have a Mobius transform which is determined by 5 points. Typically, you need 3. So maybe there could be some kind of contradictions. So here you can show that there is no Mobius transform that satisfies that because you have 5 points and typically you need 3 points. So this is like the way. So to finish, I want to just mention that I also have some null controllability result. So in that case, the control problem maps the initial data to the 0 data. And in that case, again, we have the network. We put controls in all the branches of the network except one. For here, I put control here and not here. You can prove null controllability. We have also a lot of stability results in that case. The focus is stabilization using delay, saturation, also networks where the branch go to infinity. So with respect to some further reset lines, we expect that the preprint should be soon. About the global well-posed controllability of the nonlinear system, because what I presented here is just the linear case. So we expect to get a global well-posed and also controllability for the nonlinear. A natural question is what happens with this observability when you have different lengths. This is a very complicated problem. We try a lot and it's quite complicated to study. We only have like a negative result. We can find case where the observability is not true, but a general case is quite complicated. And also motivated to that, what happened with the controllability in the critical case, which is known that for KDB equation, even if the linear equation is not controllable, the nonlinear equation is controllable. And sometimes we given some big time, but so what happened in that case of the network? And also a very natural question, it will happen if you have more general graphs, like a tree, like a tadpole, a graph with loops, and this is a very complicated question. Again, because we have different lengths in that case. So that's all. If you have more questions, you want to see a little bit more, you can go to the preprint, which is in Halon or in archive. Thank you for your attention.
Thank you very much, Hugo, this nice presentation. Please send me after that your slides.
Cool, sure.
Everyone have questions or comments, please let us know. The microphone is open. Please open the microphone for the audience. Okay, the audio is open, please. The guys have some questions, comments, go ahead. Hugo, just one curiosity, since you are the expert in graphs, you believe, for example, for the other kind of graphs, the phenomenon, because, for example, if you are in a graph like a periodic and in the, just as you mentioned at the end,
One.
Yes, just this one, okay? You imagine that we don't have any critical, no? Because it's the half line. You can check like a half line, like that. Not in bounded domain, I mean. Imagine that you have a cycle, it's a periodic one, and go on. It's like a half line. So
the problem I expect there is that if you have different notion of controllability, right? You have the KDB and the half line, you don't have exact controllability. You have a sort of exact controllability in a very weak space.
Yes, that's true. That's true.
And for the periodic part, which is if you have just imagine the KDB equation, you have exact controllability. So the question is only where you put the control.
Yeah.
So I expect you should put the control in the loop to get the exact controllability of the periodic one, and then this control go to the half line part, but then you don't have exact controllability if you put control at the left, for instance.
Right.
You have exact controllability in this very weak space. So
yes, that's true. Yes, makes sense. Nice. Okay. Thank you. Somebody have some question or comments in the audience? If not, let's say thank you again for Hugo.
Thank you for the invitation.
Okay, Hugo. I have some advertising.